Hi everybody, welcome back to the next lecture on video coding, this time motion compensation. So we all know that video coding is now becoming increasingly important because everybody is using it as part of teleconferencing, for instance, or recording and compressing videos as I'm doing it here. So it's becoming more and more relevant. Yeah, and motion compensation is an important part of the compression performance. So we already saw last time how it works. Basically, we try to predict where the current block in a current frame came from, right? And to determine where it came from, we now have an optimization task, right? We basically want to minimize the error with our motion vectors of this mean squared error or mean absolute error, for instance. So those measures tell us how similar the blocks of the previous frame are in comparison to the current frame, and we want to find the block which has the most similarity, and the according motion vector is then what we decide on, right? We take the motion vector which leads to a previous block which has the most similarity to the current block. Yeah, this argument now means we take the argument, which is this vector which leads to this mean squared error. So we are not really interested in the mean squared error, but we are interested in where it has its minimum, and that's the argument which leads to this minimum. Right. So yeah, so at this argument the mean squared error becomes the minimum. Yeah, so the next question is, how do we search the image for the best motion vector, V-min? A simple but computationally inefficient way would be to simply scan a search area. It can be an area smaller than the entire picture to reduce complexity and raster order. So here, this is depicted in this picture here. So each square here represents a block, for instance an 8 by 8 pixel block or 16 by 16 pixel block. Here this cross is our current block which we want to encode, and then we search in the previous frame in this vicinity. So we assume that this current block came from some block in the previous frame. So most likely it's actually the block in the same position if there's no movement, but if this is part of a moving object, then it's somewhere in this vicinity. So we can say we make up a search area of here 5 by 5 blocks or 4 by 5 blocks in the vicinity, and then we basically shift this block pixel by pixel over the search area and then decide at what position it has the most similarity with the current block. So unlike what's in the picture, actually we shift the current block pixel by pixel or even subpixel by subpixel over the search area. So each subpixel move represents then a different motion vector. So that already tells you that is a lot of work, right? So if you, for instance, have a 4 by 4 search area, 4 by 4 blocks, and each has 8 by 8 pixels, then we have 8 times 4, 32 pixels by 32 pixels search area. So if we have to, if we increase pixel-wise the motion vector, then we get 30 by 32, which is 1024 different positions. So that means for each block we have to try 1024 different positions. And if we now go to half pixel precision, then we have factor of 2 in each dimension, which means factor of 4, so 4000 positions. So that's a lot of work. And for each of those positions, we have to compute the mean squared error, which again consists of 8 by 8 differences squared. So a lot of computation. So if we are searching for motion vectors with pixel accuracy, we need to advance our search block pixel-wise. This is also called full search motion estimation, which leads to a relatively high computational complexity, as I just said. So to reduce the complexity, we can make the assumption that the motion vector is close to the origin with high probability, or meaning a small motion. Right? As I just said, if we have no motion, we are lucky at the same position. If we have a small motion, then it's quite close by. Hence, we can modify the search approach by starting in the origin and have a spiral-wise search path. We can then stop this search if we have some stopping criteria. For instance, reaching a local minimum or a certain threshold of the error. So this is depicted here. So this basically lets us stop the search process if we are satisfied with the similarity. For instance, if we have no motion, then the block in the previous frame at the same position will have a very low mean squared error, and that means if this is then below our threshold, then we can say now we stop, we don't need to continue to search anymore, and then we are done. So this is good because usually most of the block in the video are part of a background which is not moving, and the moving objects are only a small part of the video. Yeah, so here you can see it. Otherwise we would continue, search in the closer vicinity, and then go on to the further vicinity. And again, this would be pixel-wise or even sub-pixel-wise motions. Not as in this picture here, block-wise. This is just to make it easier to see. So we would actually have a very slow and steady motion here. Yeah, so this is the spiral order. But this approach has the problem that we can easily get stuck in a local minimum. To avoid this problem, we can apply hierarchical search order. For instance, the so-called three-step search, which is also described in the book Richardson Video Codec Design, where we start with a core search of our search area and then refine our search near the minimum of our cursor search. So this works if we have more or less smooth surfaces, not too much detail, because in this case the core search already gives us a good approximation of the similarity that we can achieve. So this is also not always working, but most often, because natural images or natural video usually don't have too much detail and contain smooth changes of brightness. So here it is depicted. So here we have search positions indicated by the circles, and we start at a high-level search here with number 1. So number 1 is the first step, or the first step of our hierarchical search. So here is our center, and then we also check the corners of our search area and the edges, and we decide which one has the most similarity. So then we say after the first step, this might be having the lowest error position here. So here the min of the first step. And then we reduce the search area, and now we test candidates number 2. So here the circles with number 2. So we are getting closer. And now assume that this number 2 is the minimum of the second step. So in the next step, we again reduce the search area, and that's number 3. And then we decide on which ones of the number 3 is the lowest mean squared error or mean absolute error. Again, keep in mind that in the pictures looks like we are just checking blocks, but in reality we are moving pixel-wise or even sub-pixel-wise. But that's kind of hard to depict in this image. Yeah, so the hierarchical 3-step search starts with a core search, which means we advance the block by more than 1 pixel, in the example by several pixels. In this way we get a coarse motion vector to the minimum of the first step, with an accuracy of a few pixels. In the second step, we set this minimum as the new center of our search and obtain a motion vector with increased accuracy, for instance 2 pixels. In the final step, we further reduce our search area and search with a final precision, for instance 1 pixel accuracy or maybe half pixel accuracy. Observe that this approach assumes that the error function is more or less smooth over the search area, which is often true for natural images. Right. Okay. So, an often used approach to reduce the search complexity is also the so-called nearest neighbor search. So, also the so-called nearest neighbor search. It uses the assumption that motion vectors don't change much between neighboring blocks. Here we choose as the start of our search first origin, which means we assume that there is no movement, and then the previous motion vector. Right? So that's another likely scenario, that the motion vector stays constant. Right? If we have an object, then usually this object is assumed to be rigid. That means blocks within this object move the same way, meaning they have the same motion vector. So that means we assume that either our current block is part of the background, which is not moving at all. So we stay in the center here, right, at the same position of our current block, or we assume that our block is part of a moving object. Then the motion vector is almost identical to the previous one. So that's shown here. So first we test the current position of the frame in the previous frame. And if that is not sufficient, then we test the previous motion vector and see if we get a better result. And also check the vicinity here. Another fast, efficient approach to find motion vectors is to use the FFT to compute a correlation function between shifted blocks. Can be seen, for instance, here in this paper, full search content independent block matching based on the fast Fourier transform from the ISIP in 2002. And for this we can observe that the mean squared error and the correlation are related via this expression here. The mean squared error is the expectation of A minus B squared. So A and B are our 2 blocks, for instance here, and the expectation is the average over the error in the blocks. And now we can reformulate it. A minus B squared is A squared minus B squared minus 2AB. And that basically is the same as first taking the expectation of A squared plus B squared, and then the expectation minus the expectation of A times B. And you can see if A and B are our 2 blocks, this is constant, right? No matter how we shift A or B, we have a more or less constant power. But this is changing. So if we have A and B different blocks, then this corresponds to the cross correlation, right? So A expectation of A times B is a correlation function between the blocks A and B. This means minimizing the mean squared error is equivalent to maximizing the correlation between the 2 blocks, provided that the energy in the blocks, the first term, stays the same. So this is also an important assumption, because often when we look at the previous block, say B is the previous block, and we go over the search area, actually this block changes. So this assumption does not necessarily be true. So in usual coders we transmit the found motion vectors to the decoder as side information. In this way the motion vectors are based on the current frame and the previous frame and have the highest accuracy. The transmission of the motion vectors needs bitrate, but usually this is more than compensated for by the savings we get from better prediction and hence smaller difference values. Right? So this is also an assumption which works for natural images, but for instance it doesn't really work if you have random pixels. So here you also need to assume that you have more or less natural images, where you have objects or backgrounds and smooth brightness changes. In principle, we could avoid sending motion vectors if we only base them on past frames. For instance, the last frame and the frame before the last frame, because in this case, the decoder could perform the same operations to obtain the same motion vectors as the encoder, but without transmitting them. But then the motion vectors would be less accurate because they're not based on the current frame, but on the previous frame. It would only work sufficiently if the motion vector does not change much. Yeah, so this leads me to a Python example as illustration. So this example shows a Python program for motion estimation with a full search in the range of plus minus 8 pixels around the current block. So this is a rather small range, and I reduced this range because it's quite computational complex. So it's a small search area, and here we can see that only 5 times 5 current blocks are chosen for motion estimation, and it's still quite slow. And this shows that the faster approaches are really necessary. So I have 5 times 5 current blocks, and for each of those blocks I have a search area of 8 by 8 pixels. So the search area is about as big as the block itself. So this is just enough to find motion that is coming from neighboring blocks in the previous frame. So let's check out what's inside. Copy. So let's open a terminal. So go to icon view, and then I can open in terminal. Okay. So now I have my terminal. Increase the font size a little bit, and then gedit the program name, and here you go. So here's the program for the motion estimation. So the beginning is pretty much the usual. Here we access the camera. Here we open a file for recording. So this is not so interesting for now. Here we have our loop, our for loop for processing the frames. So here we read in the frame first to get the shape, and if the return value is true. So here after capturing or accessing, we need to have return equals true, and this is the case if we have a camera connected. If not, then we would have false. So here we have now the processing, here the Y component, then the CB and the CR component. They are stored in this reduced array. Then we have the original displayed with imshow, here this frame, normalized to 255, and I also will display the found motion vectors here. Right, so frame vectors for now, they are 0, and here I'm using filtering for the color components before downsampling. So here capital N equals 2, so this corresponds to the usual color downsampling scheme 4 to 0. Here we have a block of 8 by 8 values, and we initialize the frame vectors with it, and now we are doing the motion estimation here. So for Y block in range of 5, so this is now the search. So this is going over the 5 blocks that we want to searching. So here now we have X block. So where's X block? Yeah, so we have two for loops. The Y direction and the X direction. So Y is vertically, X is horizontally. So each goes over a range of 5 blocks. Right, so we have 5 by 5 blocks. So here then we address the block in the previous frame by multiplying X block by 8. So this is the block index 8 plus some offset 300 here and here 200. So this basically specifies an area in the middle of our video. So just for showing more easily what is happening. So this is basically choosing an area in the middle of the frame for motion estimation. So this then looks at the current block. Y is my current block. Here we have the block index for vertical and here for horizontally. So the 8 pixels of this block. And here I'm doing now my full search with those two loops. So here you can see best mean absolute error is initialized at some high value, right? Because I want to find the minimum, so this must be high. And now I'm going over the motion vectors, the possibilities for the motion vectors. So this is the Y component of the motion vector, goes from -8 to +8. Here's the X component of our motion vector, again goes from -8 to +8. So it goes in each direction coming from the current position of the current block. And here you can see we compute the difference of the current block, Y current, so Y again the luminance, minus Y previous, and here the previous one is addressed with this offset of this motion vector. So here we have the address of the current block, and here we have this offset of the motion vector. So here the Y component of the motion vector, and here and next the X component of the motion vector. So here again 8 pixels here, and here the next 8 pixels shifted by X and Y motion vectors. So here ypref addresses the shifted previous block and compares it to the current block YC. So diff is then the difference, and the difference can be positive and negative, and that's why in the next step we have the abs of the diff. So here we compute the abs, and then we sum them all up, all pixels horizontally and vertically, divide by 64 to get the average, and then we have the mean absolute error here. Then we compare it with the previous best value, and if this mean absolute error is better than the previous best mean error, then it's assigned to best MAE. And if that is the case, we also memorize the current motion vector. So this is done in a complete search. So observe that this for loop always goes over all the 16 by 16 possibilities, so from -8 to +8. So this for loop has 16 values for X and 16 values for Y. So we have 16 by 16, it should be 256 shifts. So it always goes over all the shifts, it doesn't stop, but in the end, after we ran through all those for loops, inside MV we get the motion vector which leads to the lowest mean absolute error. Right, and remember we do that for Y blocks and X blocks, they are all in the range of 5. So for each block we do those 256 computations or trials of our motion vector. And remember, in reality you have to do this with all the blocks of your image, not just 5 by 5, right? So this actually makes it much easier for computation. So after we are done we basically can here store the image, and my motion vector block is then here also displayed here as lines. You can see here we have we display the motion vector as little lines on top of our live image. Yeah, that's pretty much it. Here I'm having my key. Maybe I should go up to, say, 50 milliseconds to leave my computer a little bit more power. So then we can try it, see what happens. So Python 3. Yeah, so here you can see an image of me, and here you can see that the motion vectors are now computed only based on the y component. So here you could see it. It's based only on the y component, this motion vector, and this is because the y component has the highest spatial resolution. Remember, the color components are downsampled. Here the color components are downsampled by this factor of 2 for compression, so the color components are not really good for a basis of motion estimation. And this is also what's really done in coders, in video coders. They base the motion vectors on the luminance component y and not on the color components. But it's then applied to all of them. So the motion vector is applied to y, CR, and CB. So this example is not really doing the compression here. It's just compressing everything unchanged. But this is how you would do it, right? You would take the motion compensated, predicted, you would take the predicted, motion predicted value or image and compute the difference, and that would be your motion compensated image, and then you would compare or compress or store this motion compensated image. Yeah, so let me do it again to see the motion vectors. So here you can see those motion vectors, and they also change according to the movement. Or when I move my head, maybe, so you should see it. And you can see those motion vectors are also seem to be not very precise. So that is also something that can easily happen, that you get motion vectors which are not really precise, or they are not really corresponding to the real motion of the image. And here also keep in mind, in this case I'm really just taking pixels, 1 pixel accuracy. So here this has an offset of whole pixels, right? So that's also kind of a restriction. So my computer is reasonably fast, so maybe I could also try to increase my number of blocks. So instead of 5, I could also try 10. See how that looks like. Okay, so now it's really slow. Yeah, so now you can easily see the effect. So this is a 10 by 10 block area, and you can see the frame rate really goes down. So that shows how inefficient this full block search is. Right? This is what's not really done. And the complexity actually gets worse with using subpixel motion estimation. Right? Recent video coding standards get much of the improved compression from subpixel motion estimation. The basic approach is to increase the size of our search image using interpolation between pixels, and then search for the motion vector in this bigger image. So for instance, if you want half pixel accuracy, we need to increase the number of pixels by a factor of 2, each horizontally and vertically, for a total factor of 4 for the number of pixels. Right? So Here the blue in this image, they represent the original pixels, and then you would interpolate pixels in between. So here the red ones are interpolated pixels. So if you here in this case have 2 pixels, you would interpolate the pixel in between by just computing the average between the two here. Same vertically and also diagonally. So here in this diagonal you actually have 4 diagonal pixels, so you would compute the average of those 4 pixels. And this computation of the average is also called the bilinear interpolation. And bilinear because it has 2 dimensions, x and y, and it's linear. So basically it's a linear interpolation. So you can imagine this if these are 2 brightness values, then the in-between values would be on a line between those 2 values. This is very simple, but it's actually not the best. But for now, we stick with it because it's simple. Actually, later standards use more advanced interpolation strategies, which we will see later. Yeah. So this bilinear interpolation computes the new pixel value simply as the weighted average of the values of the neighboring pixel values. The weighting is done using the distance. Hence, if the new pixel is in the middle between the 2 old pixels, the new pixel value, the brightness is simply the average of the values of the 2 neighboring values. Right. Or if the new pixel is in the middle or center of 4 old pixels, its value is the average of those 4 pixel values. If the new pixel is closer to one of the old pixels, its value is the weighted average of the neighboring pixels with an accordingly higher weight for the closer pixel. So that is shown here. So this is also why you can use it for interpolating more than a factor of 2, say 3 or 4. Right, so if you have a factor of 3, then you would have 2 pixels in between, so you would have to take into account the distance. So that's shown here. So here you're right in the middle, so this would be the average between the 2. Same here, but then this one here is closer to this one, so it has this value has a correspondingly higher weight than this value. So this can be also seen here in this Wikipedia link. Okay, so that's for this part of the slide. So thanks for your attention and see you in the next part.